what I would like to talk about today is some work we've been doing recently to try to develop a new type of diffractive element, which we've been referring to as optical Fourier surfaces. So I just want to remind you that in optics, we exploit only a few key effects. So we have reflection in devices such as mirrors and filters. We have refraction in devices such as lenses, prisms, and fibers. And then we have diffraction, which Sommerfeld once described as basically anything that's not reflection or refraction. And of course, diffraction leads to devices such as gratings and holograms. Now, if we want to describe all of these key optical effects in terms of a common principle, there are different ways that one can do it. The way I'm going to do it in this talk is in terms of momentum conservation. So we all know that a light wave can be described in terms of a wave vector k, which for a single frequency sine wave can basically is a vector that points along the direction of propagation of the wave. It has an amplitude 2 pi over the wavelength. And more importantly for today is that the wave vector is directly proportional to the linear momentum of the photon. So k is going to be our stand-in for momentum. Now, if this light beam impinges on a flat interface, we can think about the in-plane momentum of the process. And of course, in reflection, we know that the angle of incidence equals the angle of the output. And this is just because the in-plane momentum, kx, is conserved, where x is now the direction along the interface in this cartoon. Similarly, in refraction, we know that according to Snell's law, if we come across an interface and enter into a material that has a higher refractive index, that the light ray bends towards the surface normal. And again, this is just because the in-plane momentum is conserved. So in-plane momentum of the photons is conserved in these cases, which makes sense because the structures are invariant in x, nothing is changing in x. But one can imagine it becomes more complicated for structured interfaces. And in particular, this is when diffraction starts to become important. Now, a classic example of a structured interface is the diffraction grating. So in my cartoon here, we have this cross-sectional grooves that are periodic in X. And we know that if light hits such a diffraction grating, that its direction can be altered due to essentially interference. But we can also look at this in terms of momentum conservation. And if the grating has a period capital lambda, this sets what one calls a grating momentum vector g, which points in the direction of periodicity, again in x in this case, with a magnitude that's 2 pi over the period, or capital lambda. And so if we again consider the in-plane momentum, in addition to reflection, where the beam comes in and goes out at the same angle, and the in-plane wave vector momentum is conserved, we also have the possibility of diffraction. In particular, first-order diffraction will either add or subtract a unit of the grating momentum vector amplitude g. And so if it adds a unit of g, then this will bend the beam towards the grating interface. And if we subtract a unit of g, it will bend the beam toward the surface normal. And of course, the angles that it does this are wavelength dependent, and this is why gratings are used in spectroscopy to disperse light. Now, I'm not telling you anything you don't know. This has all been known for an extremely long time, and indeed, diffraction gratings have an extremely long history, so long that you can find these really fun papers, such as this one from 1786, entitled "An Optical Problem Proposed by Mr. Hopkinson and Solved by Mr. Rittenhouse," where they were talking about the diffractive properties of fine threaded cloths. Now, even a century ago, people were making diffraction gratings by mechanically ruling them or scratching grooves in a metal interface. Now they're more typically lithographically etched. And of course, the key parameters haven't changed. We still have a spatial period that we care about. This gives rise to these grating momentum vectors G, are also equivalent to a spatial frequency. And if we control these spatial frequencies, these Gs, then in principle, we control the diffraction of the impinging beam. And this is nicely summarized in terms of Fourier optics, where the height profile of the surface, so h, how is the height of this profile, how it goes up and down as a function of x, is directly related to the spatial frequencies by this function f of k through a Fourier transform. So the surface profile is directly related to the momentum through this Fourier transform pair of position and x and k, the wave vector. Okay, all of this is well known. So what's the problem? The problem is that due to fabrication, typically diffractive surfaces can only have 2 etch depths. So the film is either etched or it's not etched. And here's an example electron micrograph that I took from the internet demonstrating this. And this, of course, will constrain the surface profiles that one can make. And this may seem trivial, but this actually is very limiting on what we can do with our diffractive surfaces. And in particular, it leads to 2 issues. First, you're going to have unwanted spatial frequencies in your interface. And I think this is clear by considering a square wave grating. And if we try to write the surface profile in terms of a Fourier series where the height profile in X is equal to some constant offset delta plus a Fourier series of sinusoids, in this case cosines with each with an amplitude A, spatial frequency G or grading momentum vector G, and phase phi. And so our square wave grating will have the fundamental spatial frequency that we care about, but it's also going to contain many other sinusoids that we don't care about. Each has an amplitude, spatial frequency, and phase. Each contributes to the diffraction. And so we lose control of the Fourier components and then lose control of the diffraction. Now, the second issue is that in addition to having undesired spatial frequencies, we have a limited number of desired spatial frequencies. And this we can see by a simple example that let's say we have an optical waveguide and we want to add a diffractive surface to it so that we can send in red, green, and blue light and couple those photons into the waveguide. In other words, make a grating coupler for red, green, and blue photons and couple them all at the same angle of incidence, in this case, normal incidence. To do this, we need to control 3 spatial frequencies simultaneously, and this is extremely challenging with only 2 etch depths. And so a big question is, how can we address these 2 limitations of having undesired spatial frequencies and not having enough control over desired spatial frequencies? In other words, how can we better engineer the Fourier spectrum? And this is a very well-known problem. It's been known for a long time, so people have come up with clever solutions. One is just to be clever with the 2 etch depths that you have. And so just to show a few examples, you can make not periodic gratings, but make the spacing between your grooves aperiodic. And here's an example looking down on such a grating from the Feist group at ETH. And this aperiodic spacing gives you basically an additional knob to control the Fourier components. Another approach is to make so-called metasurfaces where you make little objects on your interface, subwavelength resonators that affect the phase front locally of an impinging optical beam, and then collectively all of these resonators, if they're designed properly, can control the diffraction in a desired way. Now, a second approach is to go beyond 2 etch depths, and there are different ways to do this to make multi-level surface profiles. So people have used interference lithography, where you interfere multiple optical beams in a photosensitive polymer or resist. Or there's a whole bunch of different techniques that come under the umbrella of grayscale lithography, where you try to come up with some patterning technique that doesn't just give you 2 etch depths, but multiple etch depths. Now, these approaches are powerful in principle, but so far they've really given insufficient control to allow you to make what we're targeting, which is kind of arbitrary wavy surfaces. And so if you could do this, and we would argue that you could make so-called optical Fourier surfaces where you have some arbitrary interface that can be written as a Fourier transform, or in, just to make it simpler here, to make it as a Fourier series where the height profile is a sum of sinusoids. And then you could have an arbitrary control of the surface pattern. You could have many desired spatial frequencies where you control each of their amplitude and phase, and you could eliminate all the unwanted spatial frequencies. And hopefully this would lead to more sophisticated diffractive surfaces. Okay, so if this is the goal, how can we do this? And so we've been playing with a technique known as thermal scanning probe lithography. And the way it works is basically it uses a hot tip that's on a cantilever that you can scan across an interface. And if you bring that hot tip close to a thermally sensitive polymer film and then adjust its height as you basically burn away the polymer, then you can control very accurately this interface. And moreover, because this is essentially a fancy atomic force microscope, you can use the tip motion also to measure topography at the same time and use this as feedback to control the profile you're making. And the capabilities of this tool are really amazing in the sense that in the hands of the people that developed it, here's a group at IBM Zurich, you can get sub 10 nanometer features in X and Y, so in the plane. We're going to limit our work to basically above 100 nanometer spatial resolution today in X and Y. More importantly for us is that you can have control on the height, Z direction here, with error of a few nanometers. And also, it's a really simple and flexible approach, as I'll try to demonstrate. Another huge advantage of this is kind of the design aspects, in the sense that you can use Fourier optics so that you can take the Fourier transform of a desired diffractive output. In other words, if you have a desired set of spatial frequencies that give you momentum contributions, you can include those in a function f of capital K, take the Fourier transform, and it'll spit out an analytical function for the surface profile that will do that. This analytical function can then be converted to a grayscale bitmap, and you can then feed that into the tool, and away you go. And so I'm going to start with just a simple example to demonstrate how this works by taking a single sinusoid, so a height profile that's just periodic in X. So it has an amplitude, a cosine, spatial frequency G, and phase phi, and some offset. And here is the grayscale bitmap that you can generate from this function. This bitmap is periodic in X and then constant in Y. This is a 10 micron by 10 micron pattern with 10 nanometer by 10 nanometer pixels, where you have 256 depth levels in Z that's kind of coming out of the image here. You can then take this and feed this into the tool, and you can see how well it patterns the polymer resist. And indeed, Nolan Lassaline, the doctoral student who has really been the driving force behind this project, did this over a 10 micron pattern in the polymer. And here's the measured topography in the polymer. So this is a height profile, and you can see that the polymer is actually patterned now. So that's periodic in X and constant in Y. And just to demonstrate how much control you have over this, here is a line scan from this 2D topography. So the height is a function of the distance across the line scan. And I'm going to blow this up to get a closer look. These open circles are the measured topography, and the red lines are the targeted function. So you can really get amazing control. In fact, over this whole 2D pattern on the polymer, we can measure a RMS height error of less than 2 nanometers. So you get really high fidelity patterning. Now we want to go in and measure diffractive optical effects. So what is the optical response? And to do this, we want to take the polymer and replicate it in a metal to make a metallic grating. And to do this, we're going to use a trick that we've been playing with for over a dozen years now, known as template stripping. It's really a simple concept. You're going to take that polymer profile that we've now patterned, evaporate silver on that, stick a piece of glass to the backside of the silver, and peel off the silver from the polymer and flip it over, and then you have a replica in silver now, hopefully, of your polymer Fourier surface. And what's nice is you can then use this to reuse your polymer that you've patterned many, many times to make many replicas. Now, does it work? It turns out it works extremely well. So here is that single sinusoid now replicated in silver. And blow this up, and you can see that there is some structure here, but this is the grain. These are the grains in the polycrystalline silver. Indeed, if you take a line scan using an atomic force microscope now of this structure, again, the measured topography in open circles here matches the targeted function in the solid line here extremely well. Now, this was just to get us going, but of course you're not limited to single sinusoids, so you can start playing with the Fourier components. So you can add 2 Fourier components and make a double sinusoid in silver. And here again is the measured and targeted profile in terms of a line scan across this. You can add a third Fourier component and make a triple sinusoid. And again, here's the comparison between measured and targeted function. And of course, what's nice is you control the amplitudes, frequencies, and phases of these sinusoids or Fourier components. So what can we do? I think you can do a lot of things. I'm just going to show you a few examples in this short talk of what one can start thinking about. And the first is, what type of grading does this make? So we can imagine light coming in and impinging on one of these Fourier surfaces and getting diffraction, and then measuring the diffraction efficiency of how much goes to the left and how much goes to the right in first order diffraction. And so Nolan indeed made such a structure. He had to make it deeper now to make an efficient grading, and then he measured the diffraction efficiency. So this is just how much light comes off of this surface in the green direction and the red direction as a function of wavelength. And you can see that basically half of it goes to the right in the red line, and half of it goes to the left in the green line within our experimental error. And indeed, if you add both these together, you see that this is a very efficient diffraction process. Moreover, you can start playing with your control and ask, well, can I design this Fourier surface so that the light goes all to the right? And this is known from Fourier optics that if you basically have a sawtooth grading, that this can be 100% efficient. And we could then take that sawtooth grating and simply take the first two Fourier components of that sawtooth. And here's the structure that Nolan made. And then here's what he measured. And basically, as expected, all the light, basically 100% within our experimental error, goes to the right. Very little of it goes to the left. And you can see this by adding the two components. And here around 550, or in the yellow, you're getting 100% going to the right. So you can really get efficient unidirectional diffraction or very good diffraction gratings overall with this technique. I should have mentioned, we'll just ignore this dip here. This is due to plasmons, which we're going to talk about in a second. Indeed, right now. So photons you can do much more with photons with these surfaces, not just making better diffraction gratings, but you can also start playing with coupling photons that come into surface modes, into waveguides, but also playing, as I'll demonstrate, their propagation by modulating this surface. And so the surface modes that we're going to use as our stand-in are surface plasmon polaritons that exist on metal interfaces. So imagine a metal-air interface. There are electromagnetic waves, solutions to Maxwell's equations that exist bound to the surface that are known as surface plasmon polaritons, or plasmons for short. The first question that we need to ask is, well, can we send light in and generate these surface plasmons on this interface? And to do this, we're going to start looking at dispersion diagrams, which are basically energy versus in-plane momentum or in-plane wave vector. And if we have a flat metal interface and we imagine sending photons in at some input angle theta, then this photon will give a certain amount of in-plane momentum to the interface, and the maximum amount that it can have can be defined by the so-called light line. So this occurs when the photon is basically skimming the surface. That's the maximum in-plane wave vector that this photon can provide. Of course, if it comes in at some angle theta that's not 90 degrees, then it has to be to the left here of the light line. So photons exist to the left of the light line. Plasmons, its dispersion for any given energy is slightly to the right of the light line. So photons cannot launch plasmons on their own. But what you can do is take a diffraction grating on your interface so that photons can come in with a certain angle, and you can then match the momentum with the momentum from the grating. So you can imagine that you have a photon that comes in at some angle that puts it right here in the dispersion diagram, and then adding the grating momentum, you can then take the photon at that energy and conserve both energy and momentum at the same time and excite a plasmon. And of course, this process doesn't just occur for photons coming from left to right, but also from right to left. So imagine focusing with a microscope objective. You're going to be able to see a symmetric diagram where in experiment, you'll have a range of energies that you can access, or range of wavelengths, and then a range of angles theta here, which converts into a range of in-plane momentum kx. So what we want to do now is we want to measure angle and wavelength dependent reflectivity, basically inside this blue trapezoid here, and look for decreased reflectivity. So along these red streaks, photons will go in at certain energies and certain angles and then launch plasmons, so they won't come back out, and so they'll cause decreased optical reflectivity. And these red streaks will then be a reporter for what the plasmon dispersion curve actually does, because it's basically photons that got onto this blue curve. Now, how are we going to measure this easily, though? Measuring angle and wavelength dependent reflectivity doesn't sound easy, but it turns out there's this very nice way to measure the dispersion diagram, or energy versus momentum, K, which basically boils down to measuring reflection spectra versus angle. And the way you can do this is through so-called Fourier microscopy or K-space imaging. And I'm putting an article here that describes it in much more detail if you're interested. But basically, we can measure the sample reflectivity and determine which photons, which energy, which angles excite plasmons. And the technique is you take basically an optical microscope with a white light source, a lamp, you irradiate the sample, and then measure which photons come back. And of course, if certain angles are not coming back in certain wavelengths, then that information will be encoded in this beam. All of that information is scrambled if you focus this to the image plane. But if you look at the Fourier plane, then this information is still there. So you'll have certain rings where light went in, and if it launched plasmons, won't be reflected. And these angles can be converted to in-plane wave vector along the x-axis or the axis. And moreover, you can then put your and/or imaging spectrometer at this Fourier plane and close the slits down, which I've tried to write as these parallel lines along X, and disperse the other direction, so that you can then in one shot get the wave vector along X, which is giving you angular information, and the energy or wavelength along the other axis. So you can get basically, if blue photons are not reflected at this angle and red are not reflected at that angle, all of that information in one shot can be determined, and you can measure the dispersion diagram quite easily. And this technique has really changed our lives in the lab. So just to start with a simple example, again, a single sinusoid, this single silver sinusoid, optical Fourier surfaces I showed before. You send white light with that technique I just mentioned, and you measure the dispersion diagram, so energy versus in-plane wave vector, and you see these red streaks that I mentioned before. This is the trapezoid, and these are the red streaks, the photons that went in and don't come back out because they're launching plasmons. This is giving us information about the plasmon dispersion, and because it's symmetric, I'm showing an experiment on the left and a model on the right. So these orange arcs are telling when photons that were sent in and they coupled to plasmons. They reveal the plasmonic dispersion curve, this blue line. But let's start moving beyond single sinusoids. So just one step, you can do a double sinusoid I showed you before. And now when you look at your dispersion diagram, you're going to have two Fourier components, obviously, and two coupling channels for photons to plasmons. And this is demonstrated in the dispersion diagram that you measure. Now, moreover, we have specific amplitudes, frequencies, and phases, as I mentioned before, that we control. So how can we exploit our control? And again, there are many things you can do. I'm just going to show like a fun little example here, is that we can affect how the plasmons propagate across the interface. And in particular, we can create stop bands. So we can design an interface that basically allows incoming photons at normal incidence to couple and launch surface plasma polaritons that are going to move, let's say, to the right here. And we do that through the grating having a spatial frequency G1. We can then add a second spatial frequency G2 that couples right moving plasmons to left moving plasmons. And all of that can be demonstrated in the dispersion diagram shown here, such that we would expect to see these red streaks. These are photons, let's say normal incidence would be in the center here, that with this G1 component launches a plasmon that's moving to the right. But then we have this second grading component, G2, that couples those right moving plasmons to left moving plasmons. And this then creates a stop band in the plasmonic dispersion that would then be demonstrated in these orange streaks. And the reason it's going to create a stop band is basically you can start thinking about the plasmons are interacting with each other, so that left and right propagating plasmons are going to be interconverting, and then neither can propagate. So as soon as the right one starts to propagate, it goes left and then right and left. So this leads to a plasmonic stop band, which is a range of energies for which the plasmons can't propagate because they're constantly interconverting. Okay, so this is a PowerPoint cartoon, but what about experiments? So Nolan went ahead and made such a structure. So it has these two cosine functions where he controls all of these parameters. And indeed, in experiment, he could design it such that he could observe a stop band, which of course is in the photon reflectivity, but is reporting on the plasmonic stop band. As shown here. It's kind of like having a valence band and a conduction band in a semiconductor, but now it's a stop band for plasmons. Moreover, he could then use all of his control and fabricate a series of gratings where experimentally he's varying this phase on the second Fourier component. And this is a GIF that he made of a whole bunch of gratings. This is experimentally measured topography of each of those, which he's compiled together in a GIF, where he's changing this phase phi 2, and then you can see what effect it has on the stop band. And what's fun is you can affect the coupling between photons and plasmons at the stop band edge. So you can turn one of the stop band edges dark at a specific phase, either the bottom or the top band edge. And basically using this control over the phase, you're affecting how photons and plasmons couple here. The second thing he could do, which was fun, was again to make a series of gratings where he's varying the amplitude of this second component. And again, this is a GIF of experimental data. The line is the targeted function for each of these. And as this A amplitude is getting bigger, then you can see that the structure is changing from a single sinusoid. And then here's the corresponding dispersion diagram measured through this K-space imaging. And basically he's turning this stop band on. It's going from about a 0 to a half EV. This particular one was designed not to be at the Kx equals 0, but slightly off Kx equals 0, so at an angle. And again, this just is a simple example showing that by control over the amplitude, you can start to affect how things actually work. Now, just to try to use this power to solve a problem, I mentioned that it is important to be able to couple, let's say, 3 colors of light into a waveguide mode, all at the same angle of incidence, in this case, normal. And so he designed this where the surface mode, waveguide mode, was a surface plasma polariton. Here is the particular structure that Nolan designed and fabricated. And then here is his reflectivity spectrum. So reflection percentage as a reflectivity as a function of wavelength. And here are the 3 design wavelengths that indeed are showing dips, photons not coming back because they're coupling into surface plasmons. Now, this was all, as an example, all structures that are periodic in one dimension, but of course surfaces are 2-dimensional. So you can start playing with this, looking down in terms of a cartoon here. You can imagine one sinusoid periodic straight up, and you can take another one and overlay it that's rotated by 10 degrees. And here's the particular structure that you make when you do that, where these 2 grading components are rotated by 10 degrees, so 2 sinusoids, or you can rotate them by 40 degrees, and of course the pattern will change. And then the optical response can also be measured by this K-space imaging. So taking this surface and illuminating it with white light, now the dispersion diagram, we can consider not just Kx versus energy, but Kx and Ky. So we get a 3D plot now. The photons live within not the light line, but the light cone now. And the SPP dispersion is outside that as this blue cone. And so we can take a specific energy slice through this, and we get these circles. The light cone now is this gray region, and the SPP dispersion is outside of that. So if we illuminate such a grating, we find that, of course, any photon that's along these arcs, so these are specific angles that correspond to Kx and Ky, then with the grading momentum G, will take the plasmons onto the blue dispersion curve for the plasma, take the photons and put them on the blue dispersion for the plasmons at that specific angle. And that's for one sinusoid, but if we take 2 sinusoids rotated, the second one rotated by 10 degrees, we would expect to see 2 such arcs. And that's, in fact, exactly what we see. Similarly, if we do that for 2 gratings rotated by 40 degrees from each other, then the second arcs rotate by 40 degrees, again, what you would expect. Now you can really start to play and make higher rotational symmetries. So taking 3 sinusoids here, looking down from the top, here's such a pattern. So they're rotated by 60 degrees each. This is the pattern experimentally put into the polymer. Here it is replicated in silver. So this is a hexagonal pattern. If you do that for 6 sinusoids, each rotated by 30 degrees, you get a quasi-crystalline pattern here again in the polymer. Here is replicated into the silver. And also, if you use the K-space imaging technique, then the arcs are very symmetric, exactly as you would expect. Again, these arcs are showing when the photons go in at certain angles, coupled to surface plasmons on the surface due to the gratings. Okay, so to wrap up, I've tried to talk about diffractive surfaces exploiting Fourier optics. This has, of course, been known for a long time, but patterns have mostly been limited due to fabrication to 2 etch depths. This has led to a design fabrication mismatch. And we've showed a new route to try to solve this through this arbitrarily wavy diffractive surfaces. I've shown mostly metals just due to time, but we've also shown that you can do this in dielectrics such as silicon, silicon nitride, and titanium, which are all optically interesting. So this is a silicon quasi-crystalline Fourier surfaces that we made from 12 sinusoids. And then I showed this K-space imaging technique, which is really useful, not just for these, but to measure all kinds of angle-dependent or momentum-dependent nanophotonic structures. And then we think these optical Fourier surfaces have broader implications than what I've shown you here, but I'm not going to go into that. let me finally just acknowledge, the people who did the work. Nolan Lassaline, I mentioned, really the driving force behind it, a doctoral student who's wrapping up right now. He had help from Brechbühler, another student who finished a few months ago. By coincidence, two great Dutch interns worked on this project, Sander Vonk, Cornel Ridderbeek, and then two great Dutch postdocs, Boris Lefebvre and Freddie Rabouw. All of them have moved on now. And then the tool that we use, thermal scanning probe lithography, we worked with two people from the company, Swiss Litho, which is now part of Heidelberg Instruments, Martin Spieser and Samuel Bisig. And the project was funded by ERC. This has been a presentation of the Optical Materials Engineering Lab.